All right, some of you guys were able to start on homework last night. We will go over the questions that you had on homework, unanswered. But first of all, we didn't get to totally finish, I don't think, from yesterday. We were here. And some of you guys might want to open up your homework and see what you didn't get, and then we can do an example similar. Do you have a problem number you got stuck on?
I just feel like because it said this, like 5 through 22 is like
weird.
No, it said there's like a bunch of circle ones that I did not.
Okay. Let me log in. Okay. Terminal initial, we're talking about like the beginning and ending points. Did they give you time intervals on those?
Yeah.
So then you would have used A and B as your beginning point and ending point, plugging into your x of t, y of t equations. Hey, we wrote that down yesterday. Isa, I'm coming to you. I see that hand and I value your question. Just give me a sec. Here we go. Psst, psst. Okay, Isa, go. Odd answers. Later. Oh, we haven't done that yet. How do I keep forgetting that? Summer packet, can you guys get it out? Because, yeah, you want the free 50 points towards your test. You should. Grab out your summer packets. All right, if you're just joining us, if you're listening to the video and not just getting filled in by people, hi. We don't know where you are. Deepa's skeptical. That's not the right word, but that's okay. All right, section 1.4, I have it open so that we can peek at 5 through 22. It got weird. But first of all, summer review packet. I thought that you guys might need a little bit of clarification as far as some of the solutions, particularly towards the end. So this is just your last and final call. That sounds so final. There we go. You guys, anything else that you want to hear from me about the summer packet as I pull up the answer key? Oh, do we not need anything? Do we need any clarification, corrections, answering? Yeah, Kathy. Okay. Oh, yeah. Good. Thank you for that. That was a good question. I think I might have answered it in some sort of live something or others, but it's so different when I'm doing that as far as being able to interact with you guys. So let me pull up the summer assignment. I think it was number 74. I might be totally wrong. Is it not 74? That was the one, Maggie, that you asked me about the other day. Yeah, we figured it out. It was a team effort. It's not part 2. Sorry, there is no key for part 2. It's part 1. There it is. Okay. So cosine inverse, sine inverse, tangent inverse, cotangent inverse all have restricted. Is this not right? Oh, thank you. What was 74? Oh, that must have been AB's question. Okay, sorry. Number 29. Thank you, thank you, thank you. Okay, all these inverse trig functions have restricted domains because, just think of it this way. When you plug in sine inverse, cosine inverse, tangent inverse to your calculators, they all pop out the exact same radian or degree answer. Why? There should be infinitely many answers. Because you can spin around that circle however many times and land on the exact correct location for sine to be 1/2, or cosine to be -1/2, or tangent to be -1. There are infinitely many places that can occur. How can your calculator just give one? Because the domain has been restricted. Sorry, that's the inverse. The domain of the, anyway. Domain of the original, aka the angle values, have been restricted to only be within a certain range. That's our dilemma. Because normally we say cosine inverse cosine, cross out 17 pi over 5, done. Except 17 pi over 5 is way outside of the restriction. So the problem is we would need to think if we were to solve this entirely, we would need to think of what is cosine of 17 pi over 5, which is not a unit circle value. What is cosine of 17 pi over 5? Take that cosine value and say, okay, what angle in the correct restricted range would give the exact same cosine as that angle? So We'd need to find the cosine and then go backwards, and the backwards would say, no, don't go to 17 pi over 5, only within this range. So here's the first question we have to ask ourselves: what range is cosine inverse allowed to be? Cosine will go through all of its positive and negative values between 0 and pi. That's the restriction. We have to find what angle between 0 and pi will have the exact same ratio as 17 pi over 5. So then I ask myself the question, okay, 17 pi over 5 is 3 2/5. If it's 3 2/5 pi, I can think of what location it would be in. That's 1 pi, 2 pi, 3 pi, and 2/5 pi. So I figured out that the location of 17 pi over 5 is here in the third quadrant. Cosine is negative. Where else is cosine negative in the restricted? Quadrant 2. So a negative cosine would also be present in the second quadrant, which is legal. And then I had to think of, okay, how could I go straight to that angle without doing the whole spinning thing and then going backwards? So then I thought of just symmetry. And I thought, okay, if I had 3 pi and 2/5, it was 2/5 pi past 180 or past pi. I would need to go 2 pi back from 180 or back from pi. And then I was able to think 1 pi is 5/5, 5/5 minus 2/5 is 3/5. 3/5 pi would have the same cosine value while being in the restricted range of the function. Does that make sense?
I just can't get it for some reason. I'm sorry.
No, it's okay. Does it make sense that all the answers have to be between 0 and pi? Okay, so if all the answers have to be between 0 and pi, without being able to figure out the actual cosine value of this one, I could say that this one's going to have some negative a and some negative b as its coordinate. This technically 17 pi over 5, which is 1 pi, 2 pi, 3 pi, and 2/5, is going to have this ratio where sine of 17/5 pi is b, and cosine of 17/5 pi is a. Well, I'm trying to show the negative, sorry. Symmetry in the unit circle. 17 pi over 5 would have a reference angle of 2/5, kind of like sine of 7 pi over 6 corresponds to sine of pi over 6. Does that make sense, symmetry? So then I could say, because I want to keep how in the third quadrant they're both negative, so I could say sine of 2/5 pi. So 2/5 would be the little guy over here. And so this sign, which would be like a positive number b, this cosine, a positive number a of 2/5 pi, is going to be reflected in the third quadrant whenever you eventually get to 17 pi over 5. That's going to be the exact same, but negative, negative. The problem is this guy is naturally outside of my range of 0 to pi. So then I need to think of where else, what other location would have this exact same AB, the exact same symmetry as this 2 pi over 5 in the correct restriction of 0 to pi. That will only be mimicked here, where cosine is still or also negative, but sine is positive. So I'm only looking for the cosine value. So I'm looking in between 0 to pi in that one little restricted range, what one angle would have. And the only one that's going to have it is here in the second quadrant, where it's the exact same distance apart or the same rotation away from 180. And so I take that little reference angle of 2/5 pi, how far beyond 17/5 pi is from the axis. And I say, okay, it's going to have that same symmetry wherever you go around the unit circle. That's the guy I need. And so this guy in the second quadrant, 2/5 pi up, is going to be 3/5 pi over. But if that doesn't work, what you could do is just go to your calculator and see what we basically can't do by hand. What we can't do by hand is this whole process of taking cosine, being in radian mode. This is what we're having to shortcut, taking cosine of 17 pi over 5, getting an actual value, And then saying, well, great, I know that's the value. I know that's the x, like how far over that angle falls as far as the third quadrant. I know the cosine is negative 0.309, but when you do the cosine inverse value, it says, oh, hey, I'll find for you the only legal angle I possibly can with that same cosine, 1.88495. Then we could go ahead and, this is in radians. In order to get it in terms of pi, we could divide by pi to say, what is this? This is 6.6, which would be 3/5. So that's a way of seeing like how the calculator is doing this work of taking, whenever you do cosine inverse of cosine of 17 pi over 5, it's not as simple as just canceling out. Because cosine says, hey, I'll find you the ratio. And cosine inverse says, I'll find you the angle, but only the legal one. And so this function doesn't go back to 17 pi over 5. This function goes back to the 3/5 pi. Because it's saying, okay, I'll find you the only location that I'm legally programmed able to do. That's really awkward, I apologize. I'll find you the only value that's legal in my programming. And so the only value is in the second quadrant, the angle that would have the same symmetry. Because if you were to count around the unit circle, instead of counting by sixths or fourths or thirds, we could count by fifths. And so we'd have 1/5 pi, we'd have 2/5 pi, we'd have 3/5 pi. Just put the little pi's on there, sorry, I was being lazy. We'd have 4/5 pi. We'd have 5/5 pi. And so if we were to keep counting 6/5, 7/5, 8/5, 9/5, 10/5, 11/5, 12/5, 13/5, 14/5, 15/5, somehow I got off, 16/5, 17/5. 17/5 is down there, but this quadrant is illegal. So I could go back to 14/5. Nope, 13/5. But 13/5 is also not legal. So the other way to get there is 3/5. So it's this weird, it's this weird thing of like, it's not a unit circle one, so in my head I can't actually find the cosine and then try to go back to the angle in my head. I have to figure out the location and then think of symmetry if it was cut into fifths instead of fourths or thirds or sixths. And then try to figure out it has to be an angle in either first or second quadrant with the same cosine. Doesn't have to be the same cosine and sine, just the same cosine. So yeah, it was nasty. It was gross. I think we might have to see this once this year. Maybe. Maybe not at all. It's just one of those nasty trig things that's confusing, but hopefully that at least clears it up a little bit. Good. It makes sense in mind. Sorry, in my head I was counting by fifths, but I didn't actually show that. I should have showed counting by fifths. Okay, anything else? All right, pass it up. Let's get 2 points. Let's go back to notes parametric. Thanks, Isa. So otherwise your test grade would just be your summer review quiz, and some of you guys don't like that. Aryan, ask them about the new deal with homework, giving you guys accountability, but also giving you points for attempt before grading. All right. Here we go, parametric. There are big old paper clips at the front if the staples didn't work. Yeah. Yeah. There would be no initial and terminal points, but there could still be a domain and range restriction. Because it could be like spinning in a circle, but it's not like going different locations. But the time would be infinite, so yeah, no beginning or ending. Yeah.
And then a Cartesian equation, is that really just...
That's just like function equation y equals f of x, aka eliminate the parameter. Is that good? Sorry. Cartesian equation just means function. Okay. Let's see. We talked about initial. We talked about terminal. That was a quick recap in order for you guys to do the homework. We did the example-ish. Anybody having issues putting it in your calculator? Not so far? Okay. Then let's come back to this example. We were solving it here. Any questions on eliminating the parameter when you have trig functions? Mm-hmm. The dilemma was we didn't, well, Kathy actually had a perfect question to lead us into this. We don't want to express our Cartesian equation aka eliminating the parameter, just having y's and x's. We don't want to express that in terms of any sort of inverse trig of normal trig. It's awful. Like, who knows what's going on with inverse trig of normal trig? It's confusing in a way they cancel out, but they cancel out in really weird, like restricted, having to think through all sorts of different things, ways. So as soon as we saw this t and a cosine, we were like, I hope not. I hope it's one of these nice conic sections. Conic sections almost always for parametric show up in some sort of trig being expressed in the x or in the y. I hope it's a conic section. Conic sections have nice equations, but the long story short of it is, if I could just get cosine of t alone instead of t, cosine of t alone, sine of t alone, then I can think, what property do I know that says, give me your sines, give me your cosines, I'll get rid of the trig functions? Pythagorean. So what if I was to give you another example, just to have some fun with it? What if I was to give you something like, was anybody still writing that example? Okay, I got you. There you go. What if I was to give you something like, with the same direction, get a Cartesian equation for, aka eliminate the parameter, I'll go ahead and just write Cartesian equation because some of you guys haven't gotten to homework and you're not going to know exactly why we're using that. Get a Cartesian equation for the parametric functions. X equals, let's have fun with it, -2 plus 3 secant of t. And y equals -1 plus 5 tangent. Okay. Try to apply similar logic to eliminating the parameter. What do you think I should do? Okay. So are you thinking get the trig alone? Does that kind of make sense? I got the trig alone, get the trig alone. So let's pause and do that for a second. So secant of t is equal to x plus 2 divided by 3. We okay? So what would tangent of t equal?
Y plus 1 divided by.
Yeah, you guys all good? Okay, now pause. Now we have to think, okay, what cool trig property puts secants and tangents together? Guess what? Pythagorean again, but a different Pythagorean. If Aryan was here, I'd test him on the whole, like, could he figure out the Pythagorean property? Sine squared plus cosine squared equals 1, and think, okay, what's the way of getting tangent? Sine over cosine. Divide that whole property by cosine squared. So then sine squared over cosine squared, what I'm plugging into is tangent squared. Good. So now what? Technically, that's Cartesian. It's implicitly defined, like, ew, gross, y's and x's. I mean, technically. Yeah. Now, what conic section is it? What conic section is it, Sally? What do you think? She's the closest one to pre-cal, so I was just checking. Any idea? It's okay. What if I was to rewrite it? What if I was to rewrite it? Yeah, what's it look like? She's got it. Which one? Hyperbola. Yeah. Good. Good. An ellipse would have a plus. Ellipse is like a circle, and a circle has x squared plus y squared equals whatever. An ellipse would have a plus. This one, HK, moves the center. These ones move like the minor radii, the major radii. If it was an ellipse, it would be plus. But a hyperbola, good Sally, a hyperbola would have the minus in there. And it's eventually going to be a hyperbola with the center that's shifted, and then you have like asymptotes that just define how whatever. But nice thing is we don't actually have to know what shape it is this year, but you might have to derive that. And so to derive that, did I make a mistake? Oh, no. I thought two hands. I was like, oh man. Kathy, what'd you got?
I was just wondering, does it matter, like, for hyperbola?
Yeah.
And for the formula, does it matter what is being subtracted by what in terms of x and y?
Yes, in terms of, well, first of all, in my head, real quick, I thought of subtracting this, but then this 1 would have been subtracted. So we need the 1 to always be positive. That's how I know that this is the positive one, this is the negative one, because I needed the 1 to stay positive. But once you figure that out, remember with hyperbolas, you guys turned in so many expos and I have none at the front. Oh. Nice, one of each. If, just quick recap of, that's going to be a bruise. Pre-cal. If I have x squared minus y squared equals, without going into tons of depth, 1, that's going to be, if the x is positive, they're going to be oriented right to left. If the y squared is negative, it's going to be oriented top bottom. Once you have the HKs, that moves or shifts the center. The A's and B's shifts the asymptotes. Mr. Chase should have taught you. All right. It's okay. My kids don't remember it either. Except for Sally. Kind of. But there was a lot of studying going into this test, hopefully. Yeah.
Question. So if the question were to say what portion of the a Cartesian equation is traced by the parametrized curve, what does that mean? Is it asking like what shape is it?
What's the path?
So like for that example,
So this hyperbola, which technically, since you guys are asking me anyway, it's going to be one of these guys. So I'm going to go out 3. I'm going to go back 3. No, these are the vertices to get my. And then I have to go up 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. Yeah, you guys saw conic sections in algebra 2. Go team. This Cartesian equation traces the path of the parametrized curve. Parameterized. That's so weird. It's parameterized. It sounds better. The parameterized curve. This function. This Cartesian equation traces the path of the. So it's not actually asking you to graph it, although you could graph it. You could graph this in function mode and graph that in parametric mode, and you should be able to compare the two. And besides time cutting off parts of the curve, possibly they should be the same. Does that make sense? Okay. So this gives the path. This gives the positions based on time. So maybe the thing only moves from here to here. So this is all the parametric equations would show with the right interval. But this is the overall path that it could have gone if time was long enough. So I think they're just asking for the equation. I think they're just asking for eliminate the parameter. But they're describing to you that that function, this Cartesian equation, it's not a function. I apologize, it fails the vertical line test. But this Cartesian equation does give the path for these parametric equations, the parameterized curve. Does that make sense? Okay. See how the directions get fun? Yeah, another one? Okay. It's okay, we're at the end, so if you guys are wondering why I'm answering this, it's because homework was the next, it should have been due today. But I'm being nice because I didn't go over Google Classroom and stuff. Yeah. Mm-hmm. Well, here's the nice thing. Sine squared of x plus cosine squared of x equals 1 works for t, for theta. How about cosine squared of u plus sine squared of u also equals 1?
So I just make it u.
Is it sine of 2x also, or sine of 2t also?
No, it's just sine of t and then it's cosine t.
Never mind. Okay. What problem is it? Did anybody else get to this one? Anyone else get to 21? Yeah. Okay. Let's peek at 21 real quick. We'll cover that as a homework question. Where are the directions? Naomi or Maggie, whoever has it.
It says graph the curve. What are the initial and terminal points, if any, indicate the direction which the curve is traced? That's not part of the question.
Okay.
And then it says find a Cartesian equation for a curve that contains the parameterized curve. What portion of the graph of the Cartesian equation is traced by the parameterized curve?
Okay. So it's basically saying, like, eliminate the parameter, figure out what the equation is, and just with y's and x's, no t's. So the Cartesian equation, and then figure out what portion of that, because the Cartesian equation is going to be for all real numbers. You're going to need to think of, no, only between this and this. So what's my parametric equations? And then what's my interval? Oh. Okay. Cosine 2t, you have the cosine squared minus sine squared, right? Just moving the example off to the side because it's not an example, it's homework. You're trying to get the Cartesian equations. Naomi, do you have the same thing? The parentheses aren't there? But it still means the same thing. And then the interval was different?
Negative infinity.
To 2?
Yeah.
Do you have it up to 2?
I mean, the books on my phone.
Negative infinity to infinity?
Yeah, that's what I have.
Oh, okay. Positive infinity instead.
Yeah.
Cosine squared minus sine squared. Okay, here's what I see. We can make this one. Double angle property, forever card number 1. Haha, go team. What do you guys see? I see a way of doing it. You can plug in sine. You can plug in x for sine, right? So it'd be x squared. But, I can't make sine cosine. Pause. I can make cosine squared into sine squared. How? So I could make this 1 minus, man, Arian's missing the t-proof one. But you guys are getting it. Why? Why is this good? Snap! So just because you see trig doesn't necessarily mean, right? Doesn't necessarily mean that you're fitting it into a property. It could just be rearranging stuff. I had to think of the double angle property, then I had to think of, cosine isn't sine. Oh, but cosine squared is 1 minus sine squared, and then I just substituted. So then, technically, this function is a downwards parabola. Ooh. Well, when x is 0, we have 1. And I can take a derivative negative 4x. That's my maximum, right? So then that's the Cartesian equations path. Now here's the struggle. They want to know the direction. Something probably isn't bouncing back and forth. That'd be a little weird, right? We're going from negative infinity to positive infinity. How could we figure out the orientation of this guy? You don't know parametric so hot. That's okay. T, let's plug in 0. 1, 2, 3. No. No, the t's are in trig. Don't do that. But what could you do? Negative pi, 0, pi. See if we can figure out enough. Right? If we plug in 0, sine of 0 is 0. Cosine of 0 is 1. Oh, so it's at the top at 0. Okay. At negative pi, sine of negative pi is 0. Cosine of negative pi is negative 1. But it'd be negative 2 pi. So pause. Because we would have to plug in, right, to 2. So what's cosine of negative 2 pi? Well, it's just cosine of 0, which is 1. Huh? Maybe I should have plugged in something else, like a pi over 2. Because then that would also be 1. If I plug in negative pi over 2, sine is 1. Cosine is Plug in. Have to plug in times 2. So 2 times negative pi over 2 would be negative pi, cosine of negative pi. Now it's negative 1. Huh. Plugging in pi over 2, sine is 1. Plugging in cosine of pi is also negative 1. Okay. Where does that bring us? Okay, hold on. I'm going to change colors and be like, okay, this is my parametric. So where am I at negative pi? At negative pi, I'm at 0, 1. At negative pi over 2, I'm at 1, negative 1. That must be down here somewhere. Is that right? Okay, I didn't actually graph this properly. I probably should have. Then I'm back at 0, 1. Then I'm back at 1, negative 1. Then I'm back at 0, 1. Then I'm back at 1, negative 1. Mm-hmm.
It graphed it like this, and then it went back.
Good. So the struggle is this thing bouncing? Now here's the struggle. In your graphing calculator, how can you see it bouncing? I'm not going to go through all of it. You're going to be in parametric mode. You're going to put your 2 things in. You're going to be in radians. But when you graph, you better make, because if it's tracing it over and over and over again, what's the best way of seeing it? Change him. So that you don't just see the line being the line, being the line, being the line. Make it your little circle with the tail, and then you'll see it actually bouncing. Does that make sense? So then what's the orientation? Well, the weird thing is it's just going to bounce back and forth and back and forth and back and forth. Number 21, I already have the answer key up. We can peek at it really quickly as to what this guy says. I think this is it. Section 1.4, yeah. Number 21. The t-interval has no beginning or end. It's traced and retraced in both directions. Struggle. I should have talked about how the actual path won't go forever. How or why would the actual path not go on forever? How high does sine go? How low does sine go? So can this ever go any lower than 1 and negative 1? So that's why it's cut off. But what it's going to keep on doing is bouncing back and forth and back and forth and back and forth. Does that make sense? Okay. What do we do? Made it that homework is due the way the calendar says on Monday. You guys turn it in, pictures, attempt by Sunday night. Any questions? Cool. Thanks for bearing with us as things got funny today. Yeah. Since we're doing the picture thing, it's up to you. It's up to you. I don't mind. Yeah. Yeah. But definitely shorten it and make it only per section, not each individual problem. Does that make sense? Yeah. Let me pause the video real fast. Bye, Ariane.